Nenomatica, where mathematics meets YouTube excellence. Welcome to our math video. Today, we'll solve the inequality x to the power of n over x cubed n plus 2 is less than or equal to 1/3, where x is greater than 0 and n is a natural number. Let's begin solving this inequality. We're going to use a helpful property which states that if it is greater than 0, then a plus 1 over it is greater than or equal to 2. Now, let's apply this property. Since x is greater than 0, we can use our property with x to the power of n. We have x to the power of n plus 1 over x to the power of n is greater than or equal to 2. Now, we multiply both sides by 2, giving us 2 times the quantity x to the power of n plus 1 over x to the power of n is greater than or equal to 2 times 2, which equals 4. Simplifying the left side, we get 2 times x to the power of n plus 2 over x to the power of n is greater than or equal to 4. Next, we'll use another property. The square of x to the power of n minus 1 is always greater than or equal to 0. This means that x to the power of 2n minus 2 times x to the power of n plus 1 is greater than or equal to 0. We can rearrange this to get x to the power of 2n plus 1 is greater than or equal to 2 times x to the power of n. Now, we'll combine the two inequalities we've developed. We add the left sides and right sides of our inequalities. 2x to the power of n plus 2 over x to the power of n plus x to the power of 2n plus 1 is greater than or equal to 4 plus 2 times x to the power of n. After combining like terms, we get x to the power of 2n plus 2 over x to the power of n plus 1 is greater than or equal to 4. We can further simplify by subtracting 1 from both sides. This gives us x to the power of 2n plus 2 over x to the power of n is greater than or equal to 3. Now, let's rewrite x to the power of 2n as x to the power of n times x to the power of n. So we have x to the power of n times x to the power of n plus 2 all over x to the power of n is greater than or equal to 3. This simplifies to x to the power of 3n plus 2 all over x to the power of n is greater than or equal to 3. For our final step, let's take the reciprocal of both sides of the inequality. Since we're flipping the inequality, the direction of the inequality sign changes. Therefore, we get x to the power of n over x cubed n plus 2 is less than or equal to 1 over 3. This is exactly what we needed to prove. Today we'll solve the inequality x squared plus 2 over the square root of x squared plus 1 is greater than or equal to 2. We'll follow a step-by-step approach to find the solution. Let's start by looking at the numerator. We can rewrite x squared plus 2 as x squared plus 1 plus 1. This is a useful algebraic manipulation that will help us simplify the expression. Now, we can split this fraction into two parts. The first part will be x squared plus 1 over the square root of x squared plus 1, and the second part will be 1 over the square root of x squared plus 1. Let's simplify the first fraction. The numerator x squared plus 1 can be rewritten as the square root of x squared plus 1 squared. This allows us to simplify the fraction to just the square root of x squared plus 1. Now, we can substitute this simplified expression back into our original inequality. So, the square root of x squared plus 1 over the square root of x squared plus 1 is greater than or equal to 2. At this point, we can apply a well-known mathematical inequality. If it is positive, then a plus 1 over a is always greater than or equal to 2. This is known as the AMGM inequality or arithmetic mean geometric mean inequality. Let's look at our example. If we have a plus b equals 2, we need to prove that a to the fourth plus b to the fourth is greater than or equal to 2. To solve this problem, we'll need to recall the arithmetic mean, geometric mean inequality, which states that for positive real numbers, the arithmetic mean is always greater than or equal to the geometric mean. For exponent n greater than 1, this inequality becomes more powerful. Now, let's apply this inequality to our problem. First, we recall that a plus b equals 2. According to the AMGM inequality, if we set n equals 4, we get that the quantity of plus b over 2 raised to the fourth power is less than or equal to a to the fourth plus b to the fourth over 2. Second, since we know that a plus b equals 2, we can substitute this into the left side of our inequality. So, we have 2 over 2 raised to the fourth power, which is simply 1, is less than or equal to a to the fourth plus b to the fourth over 2. Third, we simplify the left side of our inequality. 2 over 2 is 1, and 1 raised to any power is still 1. So we have 1 is less than or equal to a to the fourth plus b to the fourth over 2. Finally, we multiply both sides of the inequality by 2. This gives us 2 is less than or equal to a to the fourth plus b to the fourth, which is exactly what we wanted to prove. Let's consider our example. We're given the function y equals x plus 1 over x minus 3, where x is not equal to 3. Let's start by rewriting the function in a different form. We can rewrite our equation as y equals x plus 1 over x minus 3. Let's manipulate this to get a clearer understanding of the function's behavior. Now, we need to analyze the function's behavior in different regions. Let's first consider the case where x is greater than 3. In this region, both x minus 3 and 1 over x minus 3 are positive. If we substitute this into our rewritten equation, we get that x minus 3 plus 1 over x minus 3 is greater than or equal to 2. This comes from a mathematical property stating that for any positive number, a, the sum of plus 1 over a is always greater than or equal to 2. Let's continue with our analysis for x greater than 3. First, we add 3 to both sides of the inequality. This gives us y greater than or equal to 5 when x is greater than 3. Now let's examine the second case, where x is less than 3. In this region, x minus 3 is negative, and 1 over x minus 3 is also negative. Similarly to the first case, we can determine that x minus 3 plus 1 over x minus 3 is less than or equal to negative 2. This follows from the same property we used earlier, but now applied to negative values. Let's continue with our analysis for x less than 3. Adding 3 to both sides of the inequality, we get y less than or equal to 1 when x is less than 3. Now, let's combine our results to determine the range of y. From our analysis, we found that when x is greater than 3, y is greater than or equal to 5. And when x is less than 3, y is less than or equal to 1. Therefore, today, we'll solve a problem to find the bounds of S given a system of equations. Let's look at our example. We have a system of two equations. S equals a times b plus b times c plus a times c, and a squared plus b squared plus c squared equals 2. We need to find the bounds of S. Let's begin our solution. First, we'll apply the Cauchy-Schwarz inequality. This inequality states that a squared plus b squared plus c squared is greater than or equal to a times b plus b times c plus a times c. Using our given information, we know that a squared plus b squared plus c squared equals 2. And from our first equation, we defined S as ab plus bc plus ac. So we can rewrite the inequality as a squared plus b squared plus c squared is greater than or equal to S. For the second part of our solution, we'll use the property that the square of a sum is always non-negative. We can write that the square of a plus b plus c is greater than or equal to 0. Now, let's expand the square of a plus b plus c. When we expand, we get a squared plus b squared plus c squared plus 2 times ab plus 2 times bc plus 2 times ac, which is greater than or equal to 0. We know that a squared plus b squared plus c squared equals 2 from our given equation. Also, ab plus bc plus ac equals S from our definition. Substituting these into our inequality, we get 2 plus 2s greater than or equal to 0. Now let's solve for s. Subtracting 2 from both sides, we get 2s is greater than or equal to negative 2. Then dividing both sides by 2, we get s is greater than or equal to negative 1. Finally, combining the two inequalities we derived, s is less than or equal to 2 from inequality I, and s is greater than or equal to negative 1 from inequality 2, we can conclude that s is bounded between negative 1 and 2, inclusive. Let's summarize what we did. We used two key mathematical principles. First, the Cauchy-Schwarz inequality to establish the upper bound of S as 2. Second, the fact that the square of a sum is non-negative to find the lower bound of S as negative 1. By combining these inequalities, we found that S is bounded between negative 1 and 2, inclusive. This problem demonstrates how mathematical inequalities can be applied to find bounds of expressions based on given constraints. Let's start with our example. We have the following system of equations. A squared plus b squared plus c squared equals 1, and s equals a plus b plus c. We need to determine the bounds of S. Let's start by writing what we know about S. From the second equation, we have S equals a plus B plus C. Now, let's square both sides of this equation to relate it to our first constraint. South squared equals the square of a plus B plus C. We can expand this expression. S squared equals a squared plus B squared plus C squared plus 2 times AB plus BC plus CA. From our first constraint, we know that a squared plus B squared plus C squared equals 1. So we can substitute this into our expansion, which gives us S squared equals 1 plus 2 times AB plus BC plus CA. Let's label this as equation 1. Now, let's use an important inequality. We know that a squared plus B squared plus C squared is greater than or equal to AB plus BC plus CA. This is a reminder that comes from the Cauchy-Schwarz inequality. Let's multiply both sides of this inequality by 2. 2 times a squared plus B squared plus C squared is greater than or equal to 2 times AB plus BC plus CA. We know that a squared plus B squared plus C squared equals 1. So 2 times a squared plus B squared plus C squared equals 2 times 1, which is 2. Now, let's recall equation 1, which states that S squared equals 1 plus 2 times AB plus BC plus CA. We want to use our inequality to create a bound for S squared. Let's substitute our inequality to get 1 plus 2 is greater than or equal to 1 plus 2 times AB plus BC plus C, which equals S squared from equation 1. Let's take the square root of both sides of this inequality. This gives us the square root of 3 is greater than or equal to the absolute value of S, since we need to account for both positive and negative values when taking the square root of an inequality. Finally, we can express the bounds of S by rewriting the absolute value inequality. Since the absolute value of S is less than or equal to the square root of 3, we have negative square root of 3 is less than or equal to S, which is less than or equal to the square root of 3. Let's look at the example. We need to find the bounds of S, where S equals a plus B times the sum of 1 over a plus 1 over B minus 4, with the condition that AB is greater than 0. In other words, we need to determine what values S can take given the constraint that AB is positive, meaning both A and B have the same sign. First, we'll begin by expanding the expression for S. For this problem, we'll need to use the AMGM inequality, which states that for positive numbers A, A2 up to A, the sum of A, A2 up to A divided by n is greater than or equal to the nth root of their product. Now, let's expand the expression for S. We have a plus B times the sum of 1 over a plus 1 over B minus 4. First, let's multiply the terms inside the parentheses. A plus B times 1 over A equals 1 plus B over A. Similarly, a plus B times 1 over B equals I over B plus 1. So S equals 1 plus B over a plus I over B plus 1 minus 4, which simplifies to B over a plus I over B minus 2. Now, we'll apply the AMGM inequality to find the minimum value of the expression. For any two positive numbers, say B over A and A over B, their arithmetic mean is greater than or equal to their geometric mean. In our case, we have the two terms B over A and A over B. We know that the arithmetic mean of these two terms is greater than or equal to their geometric mean. So, B over a plus A over B divided by 2 is greater than or equal to the square root of B over a times A over B. Simplifying the right side, we get the square root of B over a times A over B, which is the square root of 1, or just 1. Therefore, B over a plus A over B is greater than or equal to 2. Now, let's determine the lower bound of S. We have shown that B over a plus I over B is greater than or equal to 2. Substituting this into our expression for S, we get S equals B over a plus I over B minus 2, which is greater than or equal to 2 minus 2, which equals 0. Therefore, S is greater than or equal to 0. Let's start with our example problem. To solve this problem, we'll use the power mean inequality, which is a fundamental inequality in mathematics. Let me first remind you of this inequality. Now, let's apply this inequality to our problem according to the power mean inequality for any positive real numbers a 1, a 2, up to am, and any positive integer n. The sum of these numbers raised to the power n is less than or equal to m to the power n minus 1 times the sum of each number raised to the power n. Let's apply the power mean inequality to our problem. We said a 1 equals x, a 2 equals y, a 3 equals c. and n equals 3. The number of terms m is 3 in this case. Let's simplify the right side. 3 to the power 2 is 9, and we're told that x cubed plus y cubed plus z cubed equals 3. So we get x plus y plus z cubed is less than or equal to 9 times 3. Now, let's take the cube root of both sides. The cube root of x plus y plus z cubed is simply x plus y plus z, and the cube root of 27 is 3. Therefore, we have proved that x plus y plus z is less than or equal to 3, which is what we wanted to show. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.